Okay, so firstly, I want to make an announcement that so because for the people who are in my GR class and they have to have an exam, and the exam is on um, so so exam of GR class. It is on May 6th, so which means next Wednesday, there will be the exam for the people who are in my GR class. So on May 6th at 10 a.m. Okay, so exam. Okay, so there's still one student coming. So let me repeat. So the exam, the final exam of the general relativity class will be next week on May 6th, next Wednesday at 10 a.m. Okay, and because of well, there's 1 week for you for preparing the exam. So I canceled the class on Friday, on this Friday. So on this Friday there will be no class, and also there will be no group meeting. Okay, for my group, for the group member of my group, because most of them they are going to take the exam. So on Friday there will be no group meeting and no class. So no lecture and group meeting on this Friday. This Friday. So let me see. Friday is, when is Friday? Friday. Today is 29. Friday is May 1st. Okay. So then the exam is next Wednesday. So the next lecture and the next group meeting will be on next Friday. So the next lecture and group meeting will be on next Friday, so May 8th. Okay, so group meeting I think will be, well, it's very much depend on Tony. So probably 9 a.m. or 10 a.m. So it will be announced later, but the lecture will be the same time. So the lecture next, so next lecture will be May 8th at the same time, 11 a.m. Okay, so this is the announcement. Okay, no lecture this Friday, but next lecture will be on next Friday. Okay, so now let's continue our studies from last time. So last time we have defined the state for loop quantum gravity, which are made by Wigner D matrices. You just have make Wigner D matrices on every edges, Wigner D functions on every edges, and you make product of all those D functions and on overall edges. And then you get a basis of our Hilbert space. That's what we learned last time. So here, okay. So well, here I better list it as a theorem about Wigner D matrices. So just to give you a summary of the property of Wigner D matrix and why they are useful and why they are important. So the reason is that the theorem is that this Wigner Well, probably this is also quite obvious if you look at the formula for the Wigner D matrix. Is that Wigner D matrix is the so-called representation matrix of SU2. Matrix of SU2 in the spin J representation in representation matrix SU2, let's say act on Vj. Well, this Vj is the carrier space of spin J representation. So this is the spin J representation of SU2. So, this is something you should familiar with that in quantum mechanics, is that your Jm basis belongs to this Vj. Okay, and then remember that this D matrix, Dj Mn, or with what we call pi J Mn H equals Dj alpha beta gamma is J M e to the minus alpha minus I alpha J3 to I gamma. Okay, so you see this is just a you can see that this is just the group of SU2, the group element H of SU2 acting on the space JV, Vj. Yeah. So this is just what we usually call the representation matrix, the representation of the group element H acting on the representation space. Yeah. So you can build this Hilbert space of spin J. Yeah. It is the space where this rotation or SU2 acting on, and how this SU2 act on this states in this space is that they are SU2 are represented as these kind of operators, this kind of unitary operators exponentiating the angular momentum. Yeah. So this is just the matrix element. This D matrix is just the matrix element of these unitary operators, and this unitary operator is so-called representation of SU2 acting on the Hilbert space, this Hilbert space. Okay, and why it is useful, because the following is actually the statement of the theorem, is that for any compact group, or let's say for SU2, the orthonormal basis, orthogonal basis, let me put it this way, the representation matrices or the elements of representation matrices, okay, form a orthogonal basis. Basis of L2 space of any compact Lie group G. So G is any compact Lie group. Well, for example, SU2. Okay, so here why representation matrices are useful here, is that there's a general theorem, general statement saying that so once you have representation matrices, and the elements of those representation matrices are clearly functions, yeah, because matrix is a matrix of numbers. Yeah? The elements of matrices are numbers, right? And but those matrices depend on alpha, beta, and gamma. Okay, depend on alpha, beta, and gamma. So those elements are actually functions of alpha, beta, gamma. Yeah, alpha, beta, gamma parameterizing SU2 group. So the elements are functions of group. Okay, and they are functions of group. And you ask the question that whether these functions somehow belongs to the L2 functions of Lie group on the Lie group. Yeah, so they are integrable or not. And the answer is yes. Clearly, they belongs to the L2 space over G. And moreover, they are actually form also normal basis. They are form orthogonal basis. Yeah, they are not clearly normalized because I show you this. Well, I write it formula again. So integral h pi j. They are not also normal but orthogonal. There is a factor is 1 over 2j plus 1. Okay, so if you multiply this pi by square root 2j plus 1, then you get also normal basis. But just the matrix element itself, it is not also normal, but orthogonal. Okay. So this is some result for the Wigner-D matrix. Why this Wigner-D matrix is very useful. All right. So now, okay. So then last time we arrived at that we have also orthogonal basis in the Hilbert space. Orthogonal basis in our Hilbert space H0 for loop on gravity and defined on the lattice gamma. So this orthogonal basis is written as T, J, M, N, okay, and depend on H on all the depend on holonomies and on all edges. So this is defined to be a product over all the edges. E belongs to the set E gamma, the set of all edges, pi J E M E N E H E. Okay. So all the labels, because you may get different pi's at different edges. So all these labels J, M, and N, they depend on pi. They depend on E. Okay. All right. So now last time I mentioned that for these orthonormal bases, they are not gauge invariant. Yeah, because under gauge transformation. So this is something we should discuss now. Is a gauge transformation of those wave functions. Gauge transformation. Remember that we have studied the gauge transformation of holonomies. So you simply plug in. So for any wave function of those holonomies, okay, so it means that this is function for all holonomies along all edges. And under gauge transformation, you just transform those holonomies. Source of E and HE, target E. Okay, so this is our gauge transformation for holonomy. Okay, so this is the, so you can, so this is just the gauge transformation wave functions. But here you can see that all the gauge transformations are at vertices. So these are gauge transformation. So gauge transformation in loop quantum gravity on the lattice acting only at vertices. Okay, so this is source is the starting point of the edge, and target is the end point of the edge. So here, so at every vertex v, and this GV belongs to SU2. Okay, so now, but this is gauge transformation. Clearly, they are gauge transformations, right? And it gives a physically equivalent state. So what we are actually looking at is some gauge invariant states. So we look at we look for gauge invariant wave function. This is very natural because physics should not depend on gauge. Okay, and in the end, we should find all those gauge invariant wave functions and get a new Hilbert space, which is the subspace of the previous Hilbert space. 0. So a new Hilbert space H gamma, which is a subspace of the previous H gamma 0, and span H gamma spanned by gauge invariant wave function. Okay, this is our A. And then these final H gamma, which what we call gauge invariant Hilbert space, or Hilbert space of gauge invariant functions, is the quantization of the Hilbert of our phase space. The quantization. Well, let's say gives the quantization, because well, it also with the quantization of a phase space, it includes Hilbert space and operators. Yeah, so we will also discuss operators later on. It's a quantization of our phase space P gamma, which is cotangent bundle of SU2 to the power P gamma modulo gauge transformations. All right, so this is our goal. Okay, so now let me look for those gauge invariant big functions. Okay, so how to construct gauge invariant wave function. Okay, so let's look at our basis. Yeah, so we are going to construct gauge invariant wave functions by making linear combination of those bases. Well, because of this reason, so our goal is to find a subspace of the Hilbert space, which only contains gauge invariant wave functions. Okay, so any state in the subspace must be a linear combination of the bases. Okay, so now let's look at a state. Okay, so now let's look at a basis. Well, let me first look at a vertex, because all the gauge transformation is acting on the vertex, right? Okay, so let's say this is a vertex V, and all the vertices are 6 valent because we are in the hypercubic lattice. So for simplicity, let me orient all the edges to be outgoing. Okay, so I assume all the edges are outgoing, and so you have around the vertices you have 6 edges. So this E1, E2, and so on, and to the E6. Okay, so you get in total 6 edges, E1 to E6. V. Okay, so now you, of course, you have other vertices and edges. Yeah, so but we only focus on neighborhood of a single vertex. Now we can have a basis. We can write down the one state in the basis is given by sum product over 1 to 6 and pi j e and e and e okay. h e e okay, and also it includes other factors because they are other part of the group, other part of the graph, which we don't consider, other part of the lattice that we don't consider in this calculation. Okay, so now let's perform a gauge transformation of this basis and see how it transforms. Okay, well, you just plug in the gauge transformation polynomials. So here we assume all the edges are outgoing. So the source of the edges are just at V, yeah, at the vertex V. So the first factor is just the G of V and HE, and then G target of E inverse, okay, and other factors. So this G target, so it will be somewhere acting on the endpoint of all those edges. So they are all different. But the point is that the gauge transformation at the vertex V is always the same for all edges. Yeah. So for all edges, there's a factor GV which is the same for all edges from 1 to 6. Okay. Now because I mentioned this pi, or pi is just the D, the Wigner D matrix. Pi j mn is just the representation matrix. Is matrix element of a representation matrix. Representation matrix. Well, so H equals to, this is just a simplified version for what I wrote above. Sometimes I just write a simplified version of this equation by consider this quantity as H hat, which is the operator version, operator representing H. Okay, and this being a representation, it satisfies the following property. So J and N. So this is the definition of a representation. H prime equals to pi j m k H pi j k n H prime. Yeah. So this is what we call representation. So here k is summed over the Hilbert space from minus j to j. Yeah. So this is by for representation. Well, this is the definition of the representation. So for what we call representation is that, and the representation matrix must satisfy this formula. Well, this formula is also easy to see here is that so pi, because of this formula, and if you look at HH prime, this is just J, the operator for HH prime. But well, this operator for HH prime is just a composition of H hat and H prime hat. Jn. Okay, and then you just insert the resolution of identity in the Hilbert space, and then you just have over K J H hat JK JK JN. Okay, and or you can also check the formula explicitly from the definition of Wigner D matrix. Yeah, so this is also doable. Okay, for those of you familiar with what we call representation, well, for those of you who have learned the representation theory, you can just follow this formula. And for those of you who don't familiar with representation theory, you can go with that, or just check from the definition. Okay, so now let's say because this pi has this property, so and then you can see this pi, the variable for the the variable for this pi is the composition of GV, HE, and G target. Okay. So now you can expand this vector. This goes below. This gives you E1 to 6 JE E LE target. Okay, and so here I skip the sum and I use the Einstein summation convention. Once I have repeat index, then it means sum. Okay, and of course there are other factors we don't take into account in this calculation. And here this is the gauge transformation for our basis. Which transforms to this new function. Okay, so now you can see that the gauge transformation of the basis is not gauge invariant. Yeah? So you go, if you do the gauge transformation of the basis, you find you get a factor at every vertex. You have a factor of depending on the gauge transformation, and another observation is that this factor is common for all edges. It only depends on the vertex because the gauge transformation is the same as a single vertex. Gauge transformation